Okay, everyone, welcome. Today I'm going to talk about uncertainty and significant figures. So this is a very new concept to a lot of people. This is where how you treat numbers in chemistry and in all of your science classes from here on out is going to deviate from how you treat numbers in a pure mathematics class. Math is the underpinning that we're using. However, it's important to understand that math is dealing with numbers as an abstract concept, and we're going to start dealing with numbers as more real world, in that these numbers come from somewhere. So it's important to understand some things about them. So one of the things that really shocks people when I tell them this is very different from a math class. So in a math class, right, if I write the number 6, right, that's the same as 6.0 or 6.000 or any of that, right? So in chemistry, 6 does not equal 6.0, does not equal 6.000. These are not the same thing. You cannot interchange them. You cannot represent them this way. And I know you may be sitting there staring at your monitor, shaking your head, wondering, what the heck is this guy talking about? Why is that the case? Because in my math class, we always did it that way. Well, that's true. Because your math class is dealing with something called exact numbers. We're not going to get to encounter exact numbers very much. Let me pose a little bit of a question to you to kind of get you thinking about what I'm talking about here. So how would you figure out how tall you are? Some of you might have some very clever answers. Sort of the one I'm expecting to get, not lots of right answers, but the one I sort of expecting is you'd get some, like a tape measure or a ruler, or go to a 7-Eleven and stand in front of the tape on the door. I don't know. But basically use a measuring device. Here's the question. Is this exact? Odds are, when you stand up next to a ruler, right, so it's the top of someone's head, probably, I guess, a bald person, right, you'll notice that there might be 5 feet, 6 feet, right? I didn't put enough hash marks there, did I? There we go. There's enough hash marks now. They're not evenly spaced. So first off, there can be some problems here. Like, one, you might not line up exactly on one of the dashes, right? Or maybe you've got a nice full head of hair. Where do I measure that exactly? There's a lot of logistical problems here, figuring out exactly how tall you are. Well, so is it exact? No, not really. Imagine if you just had if your ruler just looked like this, right? You didn't have any hash marks in between, right? Not very exact at all. Hard to get an exact. I mean, could you get a more exact measurement? Of course you could. You could measure more and more closely if your vision was perfect, measure down to the atom if you had some sort of weird superhuman vision. The idea is we can't ever get an exact measurement. I could always be more exact. Well, what could I do? I could measure with a better ruler, with more hash marks. I could get out like a microscope and look. Is there a limit to how exactly you can measure this? Well, depends what I mean. Practically, absolutely. There's a limit. I'm not going to be able to measure down to the nearest atom. And even then, we'll see later, there's some problems with that too. But so maybe theoretically I could measure down to the exact atom, but practically absolutely not. At a certain point, I have to round it off and call it good enough. I hope everybody understands what I'm saying. You know, I weigh 6 feet and 3/4 of an inch. I probably weigh actually something, it might be more like 6 feet and, trying to do my math now, and 7 7/8 of an inch or something. Who knows? I don't have a ruler that measures that exactly. So really it has to do with your measuring device. Your measuring device is the limit, also your eyesight to a degree. I'm never going to know exactly how tall I am. I can always get more and more precise. I can always parse it down to smaller and smaller fractions, right? I could always measure more precisely. The precision of the measurement depends on the measuring device. So how good the measuring device is going to limit what I know. Now back to this idea of 6 versus 6.0 versus 6.000. in chemistry, we are talking about numbers that really came from measuring devices. We actually measured them. So it's important to understand that we're going to represent the numbers in a way that also shows how good our measuring device was. So when you think of numbers in chemistry, you should not be thinking of them as 6 is exactly 6. That's not what we mean. No more than when your needle on your speedometer is at 40 miles an hour, that it's exactly 40, and I can't even draw it at exactly 40, right? You might be off by 0.00000000001 miles an hour. See what I mean? This is what I mean by exact. We can't measure that exactly. So you need to think of numbers when you see them in chemistry as 6 point question mark, question mark, question mark. This number is representing a number that was measured to the ones place, and we don't know anything better than that. This number, the second number, the 6.0, was measured a little more precisely. We know that it's 6.0, and after that, I don't know. This one is measured really precisely, 6.000 on the dot, but even after that, there might be 10 more zeros and a 1 way out here. We just have no way of knowing. So I really want to hammer home that that's where all of this stuff I'm going to talk about with significant figures is coming from, is that there's a limit to the exactness of the measurement, and we have to accurately represent that. So let's do something more, oh, that was strange. I need to animate that, and let me do a little bit of an exercise. So, sort of lost my momentum there. I had to reanimate the slide. So here's the deal. So here is this red box, just sort of floating out in the nothingness. And it, beneath it is just sort of a ruler. Forgive my crude, crappy drawings in paint. But here we go. So here's this ruler, and I'm going to have a dotted line to show where it is. So this ruler tells us where, helps us measure this the length of the side of this red box. So if we look at it, we can definitely say for sure. So the question is, what can we say using this ruler? We can say for absolute certain that the length of this box is greater than 1 centimeter. We can also say that it's less than 2 centimeters. So we know for sure it's going to be 1 point something. But it really would be kind of disingenuous of us to write 1 centimeter, because it's definitely closer to 2, and even 2. We can do better than that, right? So, but we're going to have to estimate now. So we know it's greater than 1, we know it's less than 2, but what we're going to do is we're going to estimate it to the nearest tenth of a centimeter, because I could probably figure that out. So how would I write this measurement? Well, 1 centimeter isn't specific enough, and 2 centimeters is too much. So what we're going to do is we're going to estimate. So take a moment and think about this and look and see what you guys think it is. I have my guess as to what I say it is, but that doesn't mean I'm necessarily right either. There's going to be a little variation. I say it looks like 1.6 centimeters. You might have said 1.7. You might have said 1.5. The whole point is I might be off from what you are by, a tenth of a centimeter. The whole point of this last digit that I've put down, I'm kind of guessing on a little bit. This is going to be the case with most measurements. Now, how would I increase my accuracy, my precision on this? How would I get a more exact measurement? The answer is we look at a different ruler. Notice what's different about this ruler. This ruler has hash marks on it, and these hash marks are every tenth of a centimeter. So let's see, 1.1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2. So if we look now, we can definitely see for certain, our certainty has gone way up, right? We now, on the previous ruler, we could only say that it was greater than 1, less than 2, and we guessed the 1.6. I can now for sure say that this is greater than 1.6 and definitely less than 1.7. So I'm going to end up writing it differently. My number is going to be written differently, because just like on the last ruler, it would have been disingenuous to write 1 centimeter or 2 centimeters. It now would be a little disingenuous to write 1.6 or 1.7, because I can see now that it is between 1.6 and 1.7, and I can make a reasonable guess at about what. So I'm now going to be able to estimate another decimal place out from what I could on the last ruler. So 1.6 isn't specific enough, let's say 1.63. Now, you might have said 1.62 or 1.61. That's okay. There's an uncertainty here. It's understood that we're kind of guessing on the last digit. And that's kind of the whole point. I'm showing you this because this is how measurements are taken. Even when you do like a digital balance, you'll notice in the lab that the balances, that when we're taking the masses, that last number is going to bounce up and down a lot. You're probably going to be guessing on it a lot. So it's important to know that in any measurement you ever see, the last digit is an estimated digit. It's uncertain. So that last digit is always uncertain. And it may be estimated differently. So everything else is certain. So if you see a number, 2.39945 centimeters, right? These are all certain. This last one is uncertain, or it's the estimated digit, right? There's always a guess. There's always a rounding off, an estimation in the last digit anytime you see a number. And any number you write down, you're always going to be estimating. So if you see 20.61 milliliters, all the numbers I have in red are certain, and that blue one is uncertain. So in chemistry, we record all the certain and the one uncertain digit. And it's also important that the last recorded digit tells you the size of the uncertainty. So what I mean by that, whenever you see a number like this, so there's a certain amount of uncertainty implied. By the way, this is not supposed to be a negative sign. It's just the hyphen. It's just the marks for the formatting. This is 3.00 plus or minus 0.01. So notice that this uncertainty is the same decimal place as the last digit here. This means that I've rounded my digits off to the nearest 0.01. You might see weird things like this, like 0.3, but they're really, really uncommon. Uncertainty is always in the last digit. So the last digit in any number has always been estimated. Usually, if the value of that is, so you know that if you see this plus or minus, this give or take, the place where the uncertainty is going to be is the last written digit. We write them all the way out to the uncertain digit. So you know, without even looking at this part, that the uncertainty, that plus or minus, is going to be in this last digit. Same here. Notice the last written digit is in the hundredths place, so that's where the uncertainty is. In the tenths place, that's where the uncertainty is. The difference is this is plus or minus, 1, a value of 1 in that place. This is plus or minus a value of 3. 1 is so common as a value for the uncertainty that it's not written. So if you see a number 12.1, that means 12.1 plus or minus 0.1. That's what it means. So this usually won't be written. As we saw, the degree of that uncertainty is determined by the device. So here's how it works. The uncertainty is always 1/10 the size of the smallest markings on the device. So if I have a graduated cylinder with markings every 1 milliliter, 1 milliliter, oh, sorry, that'd be 0, 1, 2, 3, 4 milliliters, then you would know that all measurements that came out of this device would be rounded off to the nearest 0.1, right? Because the markings are every 1 milliliter, so the markings are going to be estimated to the nearest 0.1 milliliter, 1/10 of 1. If you had a graduated cylinder, though, that had markings every, I'm not going to be able to do this very well, but if there were 10, the next decimal down, this is 1, 2, 3, 4, but these down here, we have markings every the markings are every 0.1 milliliters, then you would know you'd be able to estimate to the nearest 0.01 milliliters. So there's something kind of cool about that. When we look at a measurement, you know what kind of device was used to measure it. So that previous number used 20.16 milliliters. You now know that the device used to measure this had markings every, how often? Every 0.1 milliliters. That is the device that was used. And there we go. That's the device used. So that tells you what you need to know. So there's a lot of information communicated in where we round the number off. So again, you see, this is why 6 is not equal to 6.0. This was measured, depending on what units this is, so this is let's say it's mass. and 6.000. This was measured with a device that only measures, that is only demarking out to the nearest 10 grams, and your uncertainty, is plus or minus 1 gram. Your uncertainty here is plus or minus 0.1 grams, and your uncertainty here is plus or minus 0.001 grams. So the more decimal places you have, the more precise the measurement was. Okay, so anyway, so we did all that. Take a moment and take a look at these. So pause it and try this. Okay, so if a thermometer has a small scale marking at every 1 degree, that means you're going to estimate to the nearest, you're going to record to 0.1 degrees Celsius. Now that's not necessarily going to be your measurement. You might have 25.2 degrees Celsius or 16.9 degrees Celsius, but you're always going to end on that 1/10 of a degree. A cup for measuring with scale markings every 1 fluid ounce, well, you'd estimate to the nearest 0.1 fluid ounce. A graduated cylinder, these last two are tricky, and we're not going to see them very often, but I'm just putting them here to kind of bring the point home, which is a graduated cylinder with small scale markings of 0.5 milliliters is going to be estimated to the nearest 0.05 milliliters, right? 1/10 of whatever the markings are. And here, 0.02 centimeters, because it's 1/10 of whatever the markings are. If the markings are every 2 centimeters, and you're estimating the nearest 0.02. We're not going to do this in practice in the class. I just want you to understand where this is coming from. I'm not going to give you glassware in the lab where you have to do this. So, here it is. Okay, so this brings us to a concept called significant figures, which is something that students usually don't care for very much because it's going to haunt you for most of the quarter. And I'm not saying it's going to be a deal breaker for the class or anything, but it's just one of those things that takes a while to get the hang of, and so you're going to have to work with it for a while, and it's going to be sort of a constant thing we're working with. So, consider the value of the distance from the Earth to the Sun. It happens to be, for some reason, someone in my class almost always knows this, 93 million miles. And 93 million miles, here's the thing. When I write this number, this is where you get some weird ambiguity, and we're going to need some rules. So 93 million, the problem is, where did I estimate this number? Did I estimate it to the nearest mile? Because that's where the zeros go out to. But then again, if I didn't have the zeros there, it would just be 93 miles, and it would be awfully warm in the summer if the moon or the sun were only 93 miles away. So clearly these zeros just need to be there. So we need some sort of rules for understanding how precisely this is measured, right? So, was it 1 mile, is it a million miles? Where was the number rounded? We're going to use some rules for significant figures to convey this. A significant figure is just a digit that we write in a number. It's any digit that is known with certainty plus that one uncertain digit. So in the numbers I've shown you so far, it's like 20.16 centimeters. Every number there is significant. They're all significant because they're all indicating something that we know precisely. So sometimes there's some zeros that may not be significant. So let me show you. Let me show you some rules. So we have 4 rules for dealing with significant digits, significant figures. So here's how it works. Rule number 1. And so it may not be clear to you right yet where this all fits in and why this is important. Let me give you a little bit of a heads up. So for now, just bear with me on learning these rules. But what this is all about is this is making sure that we accurately represent how well we measured something. And just, you're going to have to take it as a little bit of an article of faith that we need these rules to do that. So just hang tight, and let's talk about what's significant and what's not, and what that really means for you when something is significant and is not will sort of be shown through the fullness of time, shall I say. So rule number 1 is a nice, easy one. Anything that's a number that isn't 0, so 1 through 9, That's a significant figure. It's significant. We wouldn't write it down if it wasn't measured. So 32.992 has 5 significant figures because there are 5 separate numbers there, right? It doesn't matter where they are in relationship to the decimal point. This one has 3 significant figures, 1, 2, 3 numbers. This one has 4. Okay, rule number 1 is easy. Rule number 2 and the next 3 rules are all really going to deal with zeros. Leading zeros, rule number 2 deals with leading zeros. Now, I need to make sure you understand what I mean by leading zeros. I don't mean the ones that are in front of decimal points. That's not what I'm talking about. I'm talking about zeros that are in front of other non-zero digits, of all the non-zero digits. Things that are out in front of the number. Now, you're not really going to see this unless you have something that's smaller than 1. So even 1.124, this is still a leading zero. These are all leading zeros because they're out in front of the non-zero digits. Now, regardless of where they are in relation to the decimal point, they're never significant, not ever, because of the nature of the rules we're going to use this for. It's important that when we change, so if I have 150, bad example, 153 milliliters, and I convert this to liters, that's 1.53 liters. I don't want the number of significant figures changing when I do that. So I need that to stay the same. So I don't want to start adding new significant figures. So if I had like 25 milliliters and I went to liters, it'd be 0.0250 liters. I still need it to be 3 significant figures. Okay, so that's easy. So this number has 2 significant figures. These zeros don't count. 1, 2. The 2 and the 8 count. This one has 3. The 1, the 5 count. Okay. Rule 3 has to do with confined zeros. Confined zeros are zeros that are trapped in between non-zero digits. They're always significant. 209 has 3 significant figures, right? Because if my measurement was precise enough to measure the 9, I must have measured the 0. Same thing here. These don't count because they're leading, right? 88002 is 5, so these are trapped. These are confined zeros, so they must be significant. Okay, the last rule here has to do with trailing zeros. Trailing zeros are at the end of a number. This is where we deal with that 93 million miles. It doesn't matter where the decimal point is. It matters whether or not there is a decimal point. If there's a decimal point present at any point of the number, all of the trailing zeros become significant, or the zeros carry over bars. I'll talk about that later. Otherwise, trailing zeros are not significant. So let me give you some examples, and we'll do a lot of examples here. 6.00200 has 5 significant figures. This 0 is a confined 0, so these 3 are definite. These are trailing zeros. They're at the end of the number. They're after the decimal point. So the reason that the decimal point makes these significant is if these weren't actually measured as zeros. And that's really what we're talking about with significant figures. This is I measured this. I actually measured that precisely. If I didn't measure these, there's no reason for them to be there. I would just drop them. It would just be 6.02. So these are significant. This has 2 significant figures for the same reason. 6,000 has 4 significant figures. I put a decimal point there, all the trailing zeros. It doesn't matter what side of the decimal point they're on, they're all significant. However, it's important to understand that this number is this. How many significant figures does this number have? Just 1. 1 significant figure only, just the 6. No decimal point means all the trailing zeros are not significant. So 93 million miles has 2 significant figures. What if, however, I measured 93 million miles to the thousands place? Well, that's where the overbars come in. You might see this sometimes. The overbars just tell you which zeros are significant and which aren't. If there are no overbars, remember this. Leading zeros, never significant. Confined zeros, always significant. Trailing zeros, significant. All of them are significant if there's a decimal point in the number. If the decimal point is not written, they're not significant. So 40 has only one significant number, because the 0 with no decimal point is not significant. This one, 9310, 3 significant figures. The 9, the 3, and the 1 are all significant. The 0 is not. Exact numbers are considered to have an unlimited number of significant figures. Exact numbers come from some specific places. So there are some exact numbers. Counting numbers, like there are 6 pencils in the box, or if there's 5 people in the room, because you don't have partials of that. This will also come into play when we have atoms, when we're counting up atoms. Unit conversions within the same system of units. There's exactly 1,000 grams in a kilogram, because that's how they're defined. There's exactly 12 inches in a foot, because that is what a foot is defined as, exactly 12 inches. Now, actually measuring out the distance, that won't be exact, but the conversion is exact. There's a few things when specified, but really very few. And so this is one of those few times, if I have 6 pencils in the box, an exact number is when we can actually treat it like it's a number in a pure math class, and I can just write zeros all day behind it. It has an unlimited number of significant figures. It's not 6.0000000000001 pencils in the box. It's 6. I hope that makes sense. We'll do some practice here. I hope that makes sense. Feel free to watch this video as many times as you need to. This can be a very confusing part of the class. This idea of significant figures is a new concept. So be sure to watch this again, read over everything, and come to me with questions, please. Okay, so pause and determine the number of significant figures. So this first one has 3, right, because there's no zeros to worry about. The second one, this 0 here is a leading 0. They're never significant, so there's just 4 significant figures. Here, a confined 0, definitely significant, 3. This one, trailing 0. Remember, trailing zeros are conditional. If there's a decimal point, it's significant, so there are 2 here. Here, these are leading, never significant. It doesn't matter if there's a decimal point. They're never significant, so there's only 3. Oops. Here, remember, so 1, 2, 3, and this one is definitely significant. This one is ambiguous, right, because we don't know for sure unless we look and see that there's a decimal point. Okay, fine. It's definitely significant if there's a decimal point, so we've got 4. This last one, trailing zeros again, no decimal point, and these are not significant, so there's 2. Now I'm going to look at the same exact numbers and determine the uncertainty. This is a different thing. The uncertainty, the trick of this, it's much simpler than the terminology may make it sound. When I ask you for the uncertainty, all I'm asking you to do is identify which place, ones, tens, hundreds, thousands, tenths, thousands, 10,000s, whatever, which place the last significant figure is in. That's what I'm looking for. So here, we already identified it has 3 significant figures, but that's not what we're asking here. I'm asking where the uncertainty is. Remember, the last significant figure is rounded. So here, the uncertainty is plus or minus 1. The next one, it's plus or minus 0.00001, right? 4th decimal place out. Here, it's plus or minus 1 again, right? Last significant figure. Here, last significant figure is in the tenths place, so 0.1. Here, again, it's the tenths, hundreds, thousands, 10,000ths. Here, this 0 is significant, so the uncertainty is in the thousandths. But here, this is important, and this is really what I want to jump up and down and scream about and say, make sure you see. This is not the last significant figure. These zeros are not significant at all. The uncertainty is in the last significant figure where the 3 is. The uncertainty here is plus or minus 100. Right? That's why it's significant. That's why it's very important that you're able to identify which numbers are significant and which one aren't. This is going to come into play in the next class period.